Okay, so I got some of these notes from Mr. Lynch, and I'm not sure where he got them. He might have copied and pasted them from something too, but I guess I'm the first person to use his notes, and so I guess that's why I'm giving him credit here. But you can kind of see that he's got kind of an algorithm for a lot of things. So like, if you want to find volume, you're going to have to know region. You got to know what region you're dealing with. You have to find points of intersection. Almost always, you got to find points of intersection. That can be found using the intersect button on your calculator, or sometimes just setting your equations equal to find where the two graphs cross. Sometimes you'll find that an upper function becomes a lower function. So that's what happens when two graphs crisscross like this. Right? So if that happens, you could actually have, for a portion of an interval, the black function could be considered the upper function, but for a different portion of the interval, it could be that the red function is the higher one. And so if that happens, your big R and your little r on the Washer's method might reverse. So we just typically break, anytime we have a situation like this, we sort of break it into multiple integrals and just do one part at a time. Fortunately, volumes are additive, so find the volume of one part of an object, you can add it to the volume of another part of an object. Okay, and then for volumes of revolution, I think it's really important that you draw a really good washer. That's what step 4 is saying. Drawing a sample washer is what this is talking about. Make sure you always draw a sample washer. Don't make it the biggest possible washer, and don't make it the smallest possible washer. Pick something intermediate. Okay, if you're a formula person, you like a lot of formulas, you can rely on these formulas here. A equals integral from A to B, upper function minus lower, or right function minus left. The first is for the case of finding area between two curves that are given explicitly y equals something, and this second is used when you're given two curves and it's written as x equals something, if that makes sense. Okay, and then for volumes, so these two are for area here in green. These are area formulas. For volumes, that's this disk / washer stuff. Fortunately, shells don't even show up on the AP exam at all. So that's a good thing, because you guys did struggle. Some of you struggled with shells. But here's your formula for disk. It's just pi r squared is all it is. And here's washer. It's just pi big R squared minus pi little r squared. And you can have a horizontal axis of revolution, or you could have a vertical axis of revolution. So I have seen it's like 50-50 on the AP tests. Sometimes they do the horizontal thing, sometimes they do the vertical thing. Okay. And then Mr. Lynch has a long list of possible scenarios here. So like if you keep reading, you'll see if C is equal to 0, then R is equal to an outer boundary, and little r is the little boundary. If C is a number greater than 0, then C minus the outer boundary is your bigger radius, and C minus the inner boundary is your small radius. And if C is negative, then it's sort of the other way around. It's outer boundary minus C is your bigger radius, and inner boundary minus C is your smaller. I don't really use these things. I draw a picture, and then I can see what my radii are in my big one. So this is talking about the C up here in the instructions. So right up here, there's a little y equals C. The y equals C here refers to your axis of rotation. So if everything's being revolved around y equals 1, then you would pick one of these three cases. Well, you'd actually pick C is greater than 0. You pick this second case. Like I said, I don't use any of this stuff. I just draw a picture. I figure it out as I go. Maybe that's been working for you, but if not, here are some formulas for you. Okay, and then down here, this is pretty important. Volumes of known cross sections, that just means you have an object and it's being sliced up, and every slice is a square, or every slice is an equilateral triangle. We did the Play-Doh thing where we kind of built these solids, and there are these possibilities. I don't think I've ever seen anything except these. Except for, I think, on the 2003 test, they tried something kind of creative. On the 2003 test, they mentioned a curve. I can't remember the equation right now. But there was this region here in blue, and then you had to build rectangles like this. And they said that this distance, is f of x, and this was 5 times that. Okay, this was just something they tried in 2003, and so the area of this rectangle is f of x times 5f of x. But that's the only time I've ever seen them deviate really from these basic scenarios. So you can kind of go through these. The general formula is you always integrate your area, your cross-sectional area, to get your volume. Your cross-sectional area could be squares with a diagonal in the base, in which case it would be another 1/2 in front. So you can actually write that in here. Is it in there? Leg in the base. No, that's the isosceles right triangle, though. Yeah. Leg in the base. It's half a square, though. I think we should just draw like a little sketch of each one, so you can kind of see what these are talking about again. The general idea is any solid object, okay, can be sliced up into, not any solid, but a lot of solids can be sliced, and you'll see that they form circular cross sections or something. Or maybe it gets sliced and you find, you ever had those chocolate bars that look like this? Maybe you had a Toblerone, or the black one's the best. If you slice, you see that each cross section is a triangle, right? Okay, so prism is an example of that. Or you might have like a weird shape like this, but when you slice it, you realize that the cross sections are all triangles. That'd be a very interesting looking shape, but that is possible. You can actually build these out of Play-Doh. It's weird, but you can build them. So this first one is talking about squares. So here's your curve. Maybe here's the region in the xy plane. So this is supposed to look kind of 3D here. And then you have squares standing up like this. And maybe even, this might even be where the squares are like between two curves. So like this might be the blue curve here and another blue curve like that. And then the square is sort of standing in this space, standing upright like that. So this would be the upper curve u of x, and this would be the lower curve L of x. So the length of the side of the square is u of x minus L of x. The area of that square is side times side. So it's u minus L times u minus L. U minus L quantity squared. And then since that's the area of the red, integrate it from A to B. Where A to B, of course, is the limits of integration. Notice it's dx, because these squares, when placed side by side, are one next to the other along the x-axis. So semicircle is the same kind of thing. You might have an upper curve and a lower curve, like that, but standing up in this space are these semicircles. So a semicircle, it already has area 1/2 pi r squared. The 1/8 comes from the fact that it's the diameter that you'll know. You'll know the diameter, not the radius. So there's a d over 4 that pops out from that. So the u minus L is your diameter, and then the 8 corrects the fact that you're not using pi r squared, you're using 1/4 pi d squared. But notice that this formula is exactly like the square one, with the exception of the leading coefficient. So here in the squares case, there's nothing out front, but in the semicircle case, there's a pi over 8 out front. That's the only difference. And same thing with equilateral triangle. There's a square root of 3 over 4 out front. See? And the isosceles right triangle, there's a 1/2 out front. In the hypotenuse and the base, there's a 1/4 out front. Let's draw those two so we can distinguish them. So imagine an isosceles right triangle. What is an isosceles right triangle? What is that thing? Yeah, technically it's just a 45, 45, 90, so that's a fancy way of saying 45, 45, 90. And if you have an upper curve and a lower curve, and a certain region between A and B, you could stand these up in one of two ways. You could stand it up so that the right angle is in such a way that one leg rests in the blue region. That's one way to draw it. And if you draw it this way, you'll need a 1/4 out front. Or I'm sorry, a 1/2 out front. On the other hand, if you draw it with hypotenuse in the base, it would look more like this. Here's your blue region. You've got the hypotenuse resting here, and the right angle is sort of at the top of the picture. Let me draw that a little bit bigger. Redraw that one. It's too small. So here's your blue region. Your hypotenuse is in the base. Here's your right angle right there, see? It's floating above the base. So the hypotenuse is resting on the plane. In that case, you'll just need a 1/4 out front. So it's all very formulaic, and you're welcome to memorize as many of these as you need so you don't have to hassle with figuring out the area formula for that little guy. These ones I do have somewhat memorized. Okay? And these are listed in order of most to least commonly used and tested. If everything happens to be designed this way, and this is your region, well, then you can just use this formula set on the right. So this is where your shapes, whether it's a semicircle or a triangle, these are all perpendicular to the y-axis. Okay, this is important. The way that this will be labeled on the AP exam is these would be called perpendicular to the x-axis, and these would be called perpendicular to the y-axis. Maybe you should write that down. So this is the perpendicular to x-axis. If you see that phrase, that's what they're talking about. And this is it above it? I can't see it. So, but if you see that phrase, that's exactly what it's talking about. Perpendicular to the x-axis means your shapes look like this or whatever. So there's kind of a right angle look to the x-axis there. And then perpendicular to the y-axis is the other case. So your shape looks more like this, forming a right angle with the y-axis. Okay, so I don't know how good you guys do with this, but it really is just a matter of knowing the coefficients. Okay? I'm recording this too, Brian, so anything I've said you can go back and fill in. Let's go to the FRQs. Since everything's very formulaic, you can either memorize them all, or you can just try to draw these. All of these are straight off of AP Central's website. Hopefully there's nothing secure here. I hope I didn't break any rules, but you can kind of go through these as fast as you want. You'll see that 2011 there were two forms, a Form A and a Form B, so I have both on here. That's 2000 Form A, 2011 Form A, this is 2011 Form B. They're both number 3, and both did not allow calculators. So you'll notice that they actually get down to the part C there, and it says write but do not evaluate an integral. That means you probably won't be able to do that integral by hand, and you're not allowed to calculate those problems, so we'll just write the integral for me. And I did the same thing on my test, if you remember in Chapter 7. You had to write the integral and then just stop. That didn't make it easy, right? Just because you're finishing it doesn't mean it's easy. Okay, sometimes they'll actually give you the points of intersection. Both forms of 2011's test, they gave us the point of intersection. That's nice of them. In 2003, they did not give you that point of intersection. They gave you the functions, and you had to use your calculator to get that point of intersection. So, Lauren, I think you're still finishing that test up, right? Mm-hmm. Yeah, you'll see it. You have to get that point of intersection. Without the point of intersection, there's no way to know the boundaries of integration. So, let's just go through each of these, A, B, C. Write the equation for the line tangent to the graph of f at x equals half. Okay, so you can just assume that it's going to be y equals f prime a half times x minus a half plus f of a half. So we're not into the volume stuff yet. But this is the equation of a tangent line, of course. f is 8x cubed, which makes f prime 24x squared. So if you plug in a half, this is going to be 6 times x minus a half plus f of a half. That's just going to be 1, because f of a half is just 8 times 1/8. 8 times 1/8 here. Don't forget to write the y equals, I almost forgot. But you don't even have to distribute, folks. Just leave it. Why distribute and give yourself a chance to mess it up? Okay? So just leave it like that. Okay, it asks you to find the area of R. Find the area of R. Can I erase that? Oh, I got the f of half by plugging it into here. F. Where else could I have gotten that information? F of 1/2 is 1. It actually gave it to us right here. So like I said, sometimes they give you enough to speed you up. If part A is that easy, you can trust that there's more to come. They're letting you save time here. So let's go to part B now. Find the area of the region. Okay, so this would be sort of an y equals f of x and g equals f of x kind of thing, or y equals g of x sort of thing. So I think if you're trying to pick a formula from the previous page, you would probably use the u minus l method. The idea is this: you have a rectangle in here, and the width is dx, and the height of this thing is g of x minus f of x. G of x minus f of x is the height of that rectangle, see? Both g and f change as we move along, but the difference between them is technically the height of this rectangle all times for any x. So I said that g was the upper function because I think the sine wave is actually that upper curve, you see. I think this is my sine wave up here. That's the sine. The 8x cubed, that's this lower function. Okay, so you're supposed to integrate basically from 0 to a half dx. You can tell it's a dx integral. And then you're going to be doing g minus f. So basically sine pi x minus 8x cubed. You're not allowed a calculator, so you're just going to have to go ahead and work this out. Okay, so your antiderivative is negative 1 over pi cos pi x minus 2x to the 4th. Notice that they made you integrate sine rather than cosine. My guess is because they want to make sure you know about that negative. Okay? They're going to do anything and everything to bring out the best in you. Like, that's the way this test is. If they had a choice, are they going to make you integrate cosine or sine? They'll make you integrate sine to check for that negative. They're doing everything they can to make this test as hard as possible, because they get partial credit. So if the student gets that negative, they'll just take off one out of 2, you know? So this test is extremely rigorous. Every negative, everything matters, you know? Well, in any case, you're going to be plugging in a half. Cos pi over 2 is 0, though. And you plug in a half here, and you're going to end up with 1/8, negative 1/8. So just plugging in the half gives me negative 1/8. Plugging in the 0, the cos pi x becomes 1. So you get a negative 1 over pi, but the 2x and 4 becomes 0. So now you get a minus negative 1 over pi, so plus 1 over pi. So your answer is basically this: negative 1 over 8 plus negative, or plus 1 over pi. So just watch the double negatives. Let me see. Okay, so this is our answer, and now we're going to move on to part C, where we actually do the volume calculation. I have noticed another thing. Whenever they give you a closed region, first they ask you for area, then they ask you for volume. It's been consistent for years. Okay? All right, let's go on to our next one. And like I said before, if you're scared of volume, it's pretty normal. And also, I might have scared you a little too. My tests are harder than the AP tests. Those volume problems I gave you on that Chapter 7 test were tough. I made you write a washers integral on a problem that was designed for shells, and I made you write a shells integral on a problem that was designed for washers. So I purposely switched it up and made it as hard as I could, hoping that you would find this to be less challenging. Also give you all your test points back, and so hopefully you're not too mad at me. But all the correction stuff kind of helps. Write but don't evaluate an integral expression for volume. So we're going to rotate. It's a volume of a solid of rotation. So this is not like a square or not like a equilateral triangle type problem. So you're going to wrap this thing around the line y equals 1. Okay, y equals 1 is this line up here. Really? We're going to rotate around that thing? That's going to be kind of weird. Okay, but that's what they asked for. So if you can draw a picture, that's great. That's really what you want. So I kind of need a fresh piece of paper when I do that. Here's your sine wave. Here's your 8x cubed curve. We're rotating it around this point of contact. Still didn't give myself enough room. Try again. Someday just get a huge sheet of paper and draw these real big. Y equals 1 is this line. So when you rotate around, you're going to get something like this, maybe a little too big. Like that. I can't draw very well. But this is your solid. Like that. And you're going to want to draw some loop-de-doos. So loop-de-doo means like this. So you draw a little loop-de-doo over there on the axis. That'll help you visualize the spinning. I don't think you're allowed to bring Play-Doh to the exam, unfortunately, or I'd give you some. Okay, so as you slice this thing, you're going to get washers almost always. And probably a good sample washer to draw would be over here at like x equals 1/2 or something. And then you can shade it if you want. The area of this washer is our integrand. That's the whole point. Okay? We believe this whole solid can be made of similar washers, one next to the other. So they're actually technically discs. They're not really super thin. Like they're super thin, but you need to visualize them with a little bit of thickness. So what we write is called a differential volume. What is the volume of this thing? If it has a teeny, teeny bit of thickness, well, we know that a cylinder in general has volume pi r squared h, right? A cylinder with a hole bored through it would have pi big R squared h minus pi little r squared h, where big R is the radius of the original cylinder before we cut the hole out of it, and little r is the radius of the little cylinder which we took out. So what's going on here is the height is a differential dx. It's just a teeny, teeny thickness, you could say. So for this problem, we're going to have a pi, we're going to have an r squared, and as for the h, that's a dx. The thickness is the height, dx. Since the radii are always changing, depending on which washer you draw, you're going to need to have variable expressions for these. Okay, so the differential volume is going to be pi times, and then there's going to be some kind of function for each of these guys. And this is where it gets tricky for some people. So what I usually do is, if the object is being rotated around a line that's above the curve, remember the curve originally was down here and we rotated it up into space, I will draw my radii from the line downward. Okay? So before we had ever even drawn this top part, this is our picture. So I would draw it straight down from the line of rotation. I would draw one segment from the center of the line to this point, and one from the center 2 radii. Those are your little r and big R, respectively. So something like this and this. Okay, if you're going to be finding these two lengths, they're both vertical lengths, you're going to have to subtract some y coordinates. Right? All right, so that little segment is little r. The top point right here is some point x comma 1. I don't know what x is, but it's x comma 1 for sure, is the top of that segment. The bottom of that segment is that sine wave right there. That point on the curve is the point x comma sine pi x. X comma sine pi x is that bottom point. Oops. So this is my little r segment. So how long is this segment? Should I subtract the x's or y's to measure it? It's a vertical segment. You need to subtract the y's. So what is the length of this thing? It's 1 minus sine pi x. Is that my little radius or my big radius? Yeah, in the picture it's a little one. So that goes here. It's complicated, but that's what goes there. Let's look at that bigger segment. It's almost the same idea. I'll draw it next to it. So the bigger segment, let's draw that one in green. It's nice to color code this stuff. This top point is again x1. The bottom point is not x sine pi x. It's x what? X comma what? Yes, it's that other function. So how long is this segment? Capital R. Subtract the y's to find a vertical length. What are the two y values that I'm going to subtract here? 1 minus 8x cubed. That is the length of that segment. Okay, now let's say you get it backwards, and you accidentally do 8x cubed minus 1, or maybe sine pi x minus 1. Are they going to deduct points? One minus 8x cubed squared, but then you accidentally wrote 8x cubed minus 1 squared. Are they going to deduct a point for that? No, because squaring a minus b is the same thing as squaring b minus a. So fortunately, you could get away with that. If you have these two backwards, they're not going to mark you down because the square of any distance is the square of its absolute. So it doesn't matter if it's 1 minus 8x cubed or the other way around. So you can get a little bit lucky with some of this stuff, and they're pretty generous. Anything that's mathematically true, they'll just take it, whether it looks like it means what it should or not. And so now you need to put that integral symbol back in. Basically, when you integrate both sides of an equation, you're collecting all the dv's. What happens when you collect all the differential volume washers? You get the whole volume, right? So this side is v. What happens when you collect all the pi r squared minus r squared? You're going to get all of 1. So you got to fill in that integral, flesh it out. We basically need limits of integration. Okay, so we won't go this slow on every problem. But the final answer to this problem is integral from 0 to 1. There's a pi here. This is 1 minus sine pi x quantity squared minus 1 minus 8x cubed quantity squared dx. So I don't know how hard this is going to be for you. I can actually do this really fast. I've just gotten really comfortable with this. And you can get there too. But you might not need to start grabbing large sheets of unlined paper and draw these really big, like I did, so you can see everything real clearly. Once you get your skills honed, then you won't need it. But maybe these next few weeks. Okay, I take it back. I thought that 2003 was the only time they tried something interesting here with the region of integration. But I noticed 2011 has this rectangle whose base lies in the R and whose height is 2y. That's going to be an interesting one. So we're actually done with 2011 Form A. Let's look at 2011 Form B. I actually like this problem a lot because I like the question A. And I imagine there are a lot of people who missed Part A in 2011. Let's take a look at that problem. Oops. Didn't mean to zoom in quite that much. Okay. So what is the area of this region R? You'll notice that once you get out here to x equals 4, things change a little bit. Everything after x equals 4 is just a triangle. Think we might be able to use that to our advantage when we're integrating? We could just get the red triangle right now and then do the real calculus stuff with that parabolic region, right? Okay, so why don't you guys go ahead and find the two integrals. Or even just, this is just a 2 by 2 triangle, so that area is just simply 2. So at least do the first integral. That area is 2. No doubt or doubt it. Okay, let's get that blue area though. So you're integrating rad x from 0 to 4. I like to write my rad x as x to the half. Okay, so the antiderivative is 2/3 x to 3/2. You're going to plug in 4. You're going to be square rooting the 4 and then cubing. So that's an 8. 8 times 2/3 is 16/3. Plugging in this root is nothing. Basically, you end up with 16/3, and then you're adding 2. So 16/3 plus 2 is the answer. Or you could write 22/3. 22/3. All right, let's take a look at our second part here. Okay, so this portion, I think I'll copy and paste it to another document so I can see it a little better. Let's get that picture over here too. So stretch this thing a little bit. Okay, it's saying that the region R is the base of a solid. So I'm trying to picture this goofy solid sticking out of the board at me. So there's this weird solid just protruding out of the whiteboard right now towards you, or maybe towards Mr. Milne's classroom, but it's kind of sticking out. Okay? What's it made of? What does it look like when you cut it? Well, it looks like rectangles, actually. So I'm going to try to draw this sort of from the side view. Here's your y-axis and your x-axis. Here's your curve. This is the point 4, 2. Sort of drawing this in a 3D fashion. And then there's a line like this, nice straight line that goes to 6. So a minute ago I had this shaded blue, remember, and I had this shaded red. So what we're doing is we're talking about rectangles that stand up like this. They stand upright, and they stack together to form this interesting solid. Okay? So your rectangles actually look like this. This distance here is just y, because it's the length along this So this is 2 rad x. I'm sorry, this is rad x here, and this is 2 rad x. That's if you draw your rectangle in the blue region. If you draw your rectangle in the red region, it's a little bit different. You got to be kind of careful here. You kind of need to know this curve. So can you think of what is the equation of a line that goes from 4, 2 to 6, 0? You kind of need that equation because that's going to be your y value, which in turn will be the side of this little rectangle, see? So you need to know this equation, just like you knew this was rad x, you need to know what this line is here. Yeah, question?
Does it say from perpendicular to the y-axis?
Oh, shoot, I drew them wrong, didn't I? Mr. Shore drew them perpendicular to the x-axis. I think it's good for us that I did that wrong, actually. For one, because it tells you what not to do, but also because the integral is actually going to be easier now. Thank you, Lauren. Here is our drawing. Here's our blue region. Here's our red region. We were supposed to draw our green rectangles this way. Like that. Okay, so this distance is 2y. Thank you. Okay, so that means we're going to have to figure out the length of this base in here, which means we're going to need to know the endpoints of that segment. So without the coordinates here and here, we will not be able to find the length of that base. So now it's time to kind of figure out these coordinates. So this point is x rad x. Can you think of another way to write that instead of x comma rad x? What's another way you could write that? I got to teach my pre-calc kids this stuff this year. This point right here can be labeled x rad x, but there's another way you could label it. Instead of x rad x, y squared y. To say that the x is the square of, since x is the square of x squared, I'm sorry, x is the square of square root of x, if this was labeled y, then this would be y squared, you see. This is something I've got to teach my pre-calc kids this year, so don't stress about it next year. Having x f of x here is the same thing as having f inverse y here. Same thing, same point. Okay. Which do you think would be better, to have y squared y or x rad x? You guys think about that. It's probably going to work out better for us to have y squared y, but we can vote on that later too, after we have our integral sort of formed. Let's go over here and label this point. Notice that this is just a line right here with a slope -1, and it passes through the point 4, 2. So this line right here, I never actually wrote the equation for it, but it's negative x plus 6 is what it is. So I just kind of labeled that off to the left here. This is the line negative x plus 6. So you can label this point as x comma negative x plus 6, or you could label it how? Something comma y. Can you think of how to label it as something comma y? 6 minus y. You're right. 6 minus y. So what we usually do to get that is you take this expression here and you isolate x. So x is 6 minus y. See? Okay, so now we can write down the area of this green slice. So the area of this green slice is height times base. It makes more sense to me to use for my length here the difference between the x coordinates. So I can either use x minus x, I'm sorry, I can use either, yeah, I actually have to use 6 minus y minus y squared. I don't really have a choice. I was trying to debate which coordinates I want to use, but I can't use x minus x, right? So I'm going to be using 6 minus y minus y squared. That will be the length of that segment. 6 minus y minus y squared. 6 minus y minus y squared. That becomes our area, our differential area. Okay, and then you can kind of visualize this as sort of a sheet in space. So if you give it a little tiny bit of thickness, there's a little bit of dy thickness to it. So our differential volume, I'll just write at the top of the board here, is dy equals length times width times height. And this is what you would integrate both sides of to get your volume. Obviously, we're integrating from 0 to 2. 0 to 2. Because y equals 0 is the smallest y in this problem, and 2 is the largest. So in other words, the range of this visible region is 0 to 2. Okay, do they ask us to solve it, or do they just ask us to integrate it? Or just write it? Looks like it says write, but do not evaluate. So fortunately, we can stop that. It's a tough one, isn't it? They say the Form Bs are harder than the Form As, but I don't know. That's what I've heard. Okay, let's go back and look at part C, I guess. We certainly don't have to do all these problems. It's just there for you to have a nice packet too to work on. So you have all these questions in one position, one place. All right, here's part C. They're very good at writing questions. So it says there's a point P on the graph of F tangent to the line at which the line tangent to the graph of F is perpendicular to the graph of G. Find the coordinates of this point. It's a very creative question. Do you understand it? There's some point on the graph of F where the tangent line is perpendicular to the graph of G. What's it talking about? Graph of G is over here, isn't it? Can someone tell us what is it they're talking about? Elizabeth, can you tell me what are they talking about? Somewhere there's a tangent line perpendicular to the red? Yes, there's lots of tangent lines on f of x. What is this question claiming? What is it asking us to do? There is a tangent line at 4, 2. Do you think it's tangent, or do you think it's perpendicular to the red line? Probably not, right? So what do you think this question is actually asking for? Is it asking for the tangent line at 4, 2? I don't think so either. They're really interested in a very specific tangent line. We don't know where it is. That's the whole point. We're going to try to find which tangent line it is. I'll bet it's this one. You know? It might be at x equals 1 or something just shy of 1. Does that make sense? Okay, so that's what we're seeking to find is this point right here, xy. That's what we want. Okay, so if two lines are perpendicular, then we know that their slopes are what? Opposite reciprocals. So we already know that this line has slope -1. It basically goes down 2, right, 2. Okay, which means we're wanting our blue line to have a slope, what? 1. right? We want opposite reciprocal. But it's the slope of a tangent line. So we want f prime of something to be 1. F prime of something is 1. What is the derivative of rad x? Yeah, f prime is 1 over 2 rad x. So we're seeking some point A, some value of A that makes this statement true. And I believe the answer is 1/4. So A equals 1/4. It's probably even a little further over than I thought. At first I thought it was close to, x equals 1, but I don't think so now. It's over here at x equals 1/4. And that tangent line makes a nice right angle there. Is that what they asked for, the x coordinate of the point? What does it say? Find the what? Coordinates, plural, right? So we owe them a y coordinate too, don't we? So 1/4 is the x, square root of 1/4 is the y. The answer is 1/4, 1/2. So these guys are really good at writing questions. They're just, the sky's the limit. They're very creative test writers. I always appreciate that, having written tests for so long. Never even come close to their creativity level. So, but it really makes you think, and that's the whole point. Okay, that's 2011, and you'd be given 15 minutes for each of those. Okay, so what I thought we could do is just kind of scan through some of these others and let you pick one more we could try. There's so many to choose from. Or you can just ask generic questions like, sure, on this question, should we try this or that or whatever. Look for variety as you scan through the packet. Look at the calculator ones and see how they differ from the non-calculator ones. Do I have any calculator ones? Yeah, the 2007s are you're allowed a calculator. Read through the questions. Is there anything that stands out to you? Something you'd like me to go over? Well, you guys aren't really asking, but I did notice something about the 2007 questions. First of all, the calculator is allowed. So that means you have an added bonus. You can do your integrals on the screen. However, there is a drawback. They're not going to feel obligated to give you points of intersection. Right? They don't owe you anything. So look at Form B, for example. This might be, if we're going to do one more together today, this might be it, It's a calculator problem. There's no boundaries of integration given, except maybe, it's -1 to 3 or something. Why don't you guys go ahead and see if you can figure out part A. It's kind of a tough one. So you draw some sample rectangles up there in region R. You realize you're really only integrating between these two red endpoints right here. And it's kind of like this is your your x-axis here. So you really kind of need to figure out what the equation of this blue line is and what the equation of this red curve is. Your sample rectangle fits nicely right in here, see? So I believe this is the y equals e to the 2x minus x squared, I would assume. And this is just the y equals 2 line. So you're going to be integrating upper curve minus lower curve. But you need the a and the b. You need those points of intersection. So you're just going to have to use your graphing calculator. Or you can try setting e to the 2x minus x squared equal to 2. You can try that by hand if you want. Sometimes it works out. Let me try that in green here. We'll see if it's a dead end. I'm going to take e to the 2x minus x squared and set it equal to 2 in hopes to find x.
Are you trying?
Yeah, I tried it. You get
How do you solve this by hand, you know?
a non-factorable.
Yeah, you're going to get an ln. Basically, you get 2x minus x squared equals ln 2. So even if you're macho and think you're all cool and trying to show up, you can try to isolate x using quadratic formula, but you're still going to need a calculator to get the decimals, right? So forget that. Let's just go ahead and get those 2 points of intersection from the screen. So we got to kind of review that. Most of you guys know this already, but my pre-calc students are still picking this stuff up. Okay, so we're going to do e to the, put it back in funky mode if you still have it in polar mode from the other day. So 2x minus x squared, and then the other one is y equals 2. And you can just do a zoom standard. Alright, so let's zoom in once. So where are these crossing points? That's what the intersect button's for, right? So you just do intersect. Y1 is the exponential curve. Well, it looks more like a bell curve. And then Y2 is the y equals 2 line. And I don't ever guess. It just says 0.446. So I'm going to store that now. This is the last thing my calculator did, right? My calculator just found this. So this is now saved under the ans button. Answer, right? So like if I go to my home screen and I just type, what was the last answer? Can't remember. The calculator remembers. The calculator just found that point of intersection for you. So let's store this as alpha A. So store as alpha A. That way I never have to write it down. Okay, let's go back to our graph. Let's find that other point of intersection. Y1 is the bell curve, Y2 is that line. This time we'll have to guess a little. Just get it a little closer to that one on the right so I can help the calculator find it. 1.5539. Let's check our answer button. Yep, there it is. Let's store that as alpha B. So isn't that nice that the calculator remembers the last thing it did, even if it was from the graphing screen? So A and B are safely stored. And I don't know whether you're supposed to write them on here or not, but if you want to, you can put 446. Just do the nearest thousandth thing, you know, and 1.554. Technically, they didn't really say write an integral, so you could do almost everything on the screen. Okay, let's type it. So we're going to do math 9. We're going to do y variables and do y1 minus y2, which is kind of silly because it's really just 2. And we're integrating with x as an independent variable from alpha A to alpha B. So this is just ridiculously accurate because we stored alpha A and alpha B, and it's 0.5141. So we'll just go with nearest thousandth, 0.514. Yeah, question?
On the AP test, if you don't store the variables, will you be off to a degree large enough that they would like mark you down that you're not the real answer?
If you write down 1.554 and 0.496 rounded like that, and then you type this in, you will be off you'll be off, I believe. Did it work for you?
I just wrote down the decimals and then I got the right answer.
And it came out even nearest thousand, huh?
It came out to 0.514.
Okay,
But
great.
It doesn't show all the digits when it on that little screen.
I don't know, it just seems a little risky to me. If you wrote down 1.554 and 0.446 and you try to plug those in by retyping them, it might be accurate enough, it might not. You might lose that sig fig there, and you can't. You're not allowed to. So, what were you gonna say?
I got, just by doing the decimals, I got 0.514142777.
So it's
And what
accurate
did-
even to the nearest 100,000.
Right.
Okay. Yeah, I don't always to know, what's my truncation error going to be, so I just don't take any chances, and I'll take the time to save those A and B.
It's faster anyway.
But yeah, it looks like it's more accurate than even needed when you did it your way, so, yeah.
So you don't have to like actually integrate that, they're fine if you just type it in your.
Yeah, I don't think there's any human on earth that can integrate e to the minus x squared, let alone e to the 2x minus x squared.
Just make it.
No, I know what you mean. So Newton would have given, probably his entire desk drawer full of cool stuff he solved to get a calculator. I mean, look at what the calculator did for us. It's amazing. So that's that area of region R. How would you find region S? They thought it was important enough to dedicate part B to it.
Split it into
Yeah.
three units.
You would integrate from where S intercepts the line y equals 1.
Okay, that point should be pretty easy to find.
Yeah.
Yeah.
1 and then 2, or 2, 1.
These are probably just the points 0, 1, and 2, 1. You can easily verify that by plugging in x equals 0 and x equals 2 into here, and you'll see they both come out to 1. Okay, so what are you saying about those 2 points?
So you would integrate e to 2x minus x squared from 0 to 2, and then you would have to subtract your area of R and your square underneath from 0.
Okay, so you're planning on just integrating like this. So we're done with part A. So she just wants to integrate from 0 to 2, the e to the 2x minus x squared. And that's going to give you all that area in black. And you said we also then would need to take out,
Subtract R, and then that
you got to take this out, and you got to take this out up here. Yeah, you're right, that would work. So to get that black area, you'd basically integrate everything, and then just subtract out that 2 by 1 rectangle, and subtract out the 0.514 that you got a minute ago. Great, yeah, that's the problem solving they're looking for, right? So something like that would work. So take this minus the 0.514 from the previous problem, right? Minus, and this is just a 2 by 1 rectangle. Yeah, so let's go do that on the screen. So you would be basically doing math 9, vars y1, independent variables x. We're integrating from 0 to 2. We never really verified that those are exactly the right points, but you can later. And then we'll subtract off the previous answer, which is the 0.5141, and we'll also take away 2. So the answer here is 1.546. 1.546. That. Okay, and then part C, we're on to that volume thing. So we're going to be rotating the region R around the line y equals 1. So nice big drawing here. Region R is up here. You're going to rotate that around the line y equals 1. So what's going to happen is it's going to end up down here. So this is region R spun around the line y equals 1. So which method would be appropriate for this? What is this thing? If you draw a sliver or a slice, what is that thing? It's a washer. It's a disc with a disc taken out of it, right? Okay, so it's definitely going to have a pi. It's definitely going to be an integral. It's going to be from that old a to that b that the calculator has stored. It's going to be capital R squared minus little r squared dx. And now it's just a matter of finding the 2 green segments that we were finding earlier. Let's do green and blue. So we have green for the little guy this time, blue for the big guy. Let's look at that little radius. So that little radius runs from a point on the line y equals 1. So this is the point x comma 1, all the way up to, and notice that the top of this green segment is really just the y equals 2 line. So x comma 2. So how long is this green segment? 1. It doesn't matter where I slice it. So little r is 1. Doesn't matter where you slice, that inner radius will always be 1 because it's cylindrical over there down the center. Okay, and then the blue one there. This top point is x comma e to the 2x minus x squared. This bottom point is x1. So how long is that segment? The difference in y's, right? So e to the 2x minus x squared minus 1 is how long the blue is, and that's your big radius. So we have e to the 2x minus x squared minus 1. And the only thing that I was going to say, the last thing I was going to say was, there's like a top 10 things that people do wrong in the AP test. And one of them is, instead of people individually squaring the r's, they have them both together and then they square. This is like number 3, top error on the AP exam. So instead of r squared minus r squared, they have r minus r quantity squared. So they have the ones already like combined and they have like a 2 there they're trying to square. That's not what you do, right? You're going to be, if you have to type this thing, you're going to type it as is. Don't try to combine the 2 parts of the diagram unless you carefully FOIL everything, right? Okay, so there it is. Now if you were to go back and look at those formulas back on page 1, you would see that this formula, for example, fits perfectly with Mr. Lynch's formula. Everything works out great with whether you use formulas or your drawings. Okay, so I'm actually done. I don't have anything else for you except these practice problems, you know. I was just going to upload this to YouTube and then take off. Does anyone have any questions, though, before we go? Well, the limits of integration are the same a and b that my calculator had stored earlier. So I probably should write those down for the grader, right? We don't want the grader to know what a and b are. They shouldn't have to know that. What are they again? 0.443 and what was the other one?
6 and
Oh, sorry, 446 and what?
1.554.
Yeah, thank you. So, yeah, for sure, write them in there. All right. Any other questions? All right, thanks for...